Welcome to today's lecture on fluid inclusions in minerals, and this is the concluding part of the second module of the lecture series, in which we plan to get ourselves introduced into the principles of microthermometry, and we will be discussing which one of the very important and crucial aspect of fluid inclusion study, that is fluid inclusion petrography. As you will see, when this will be more of it, as we will be going through many of the case studies on various situations like ore forming environment, metamorphic environment or deformation, and so on and so forth. So, we will be continuously reiterating many of the aspects or many of the situations in which we will see that the fluid inclusion petrography actually constitutes the backbone of the fluid inclusion study. And to be honest enough, it will be difficult to really tell that that whatever could be discussed here, there could be many more things to it, and it will possibly cover a whole course to discuss about fluid inclusion petrography, taking many of the exceptional situations, many of the uncertainties, many of the curiosities, questions that all arise during the study of fluid inclusions. Again, we will try to put things in a very simple manner. So, if we talk about fluid inclusion petrography, so let us say that it is okay, it is anything like very akin to or similar to what we know as petrography of rock. But before that, let us be reminded of the fact that we study fluid inclusions in sections, which we call them which are the doubly polished thin sections. We call them as wafers, or they can be called as fluid inclusion sections. They are the fluid inclusion section, means the wafer that we have made about maximum up to 300 micron in thickness, and depending on the nature of the sample, sometimes we have to make it a less thicker or a little thinner than 300 microns, depending on the clarity, visibility of the host mineral that we are considering. In any case, a fluid inclusion section is the thing that we begin with, but then sometimes it would be a good practice to also have to study that particular, depending on the problem that we are addressing, either it is an ore specimen or a rock. It is always good practice to study a normal thin section and then see whether in a normal thin section, because normal thin sections are 30 micron in thickness, it is also still possible to observe fluid inclusions in such kind of thin sections, which will give us some guideline that which are the kind of samples which will prepare the fluid inclusion sections can be prepared, so that we could see some better inclusions there or better population of inclusions in those samples. So, it possibly would be a good practice, but then if the problem has been defined that we are going to study fluid, then we can also, under certain circumstances, since for example we are going and looking at quartz veins of different generations, and we sample the quartz vein, and we need to study fluid inclusions in quartz veins, and it possibly would be a situation where you can directly can prepare a fluid inclusion section, but in most other cases it would possibly be wise to look at the thin section and be aware about the occurrence of fluid inclusions in those sections. Now, in the beginning, if you remember, we discussed that fluid inclusion study actually the beginning is made very much during the time that we are doing the field work. We have defined the problem that we are trying to address, the issue of origin and evolution of the fluid in any environment. So, it is one of the experts in fluid inclusions, Jacques Touré. So, he says that studied fluid inclusion must be well located. So, well located in the host crystal in the thin section in the hand specimen, and hand specimen in the exposure. So, this itself tells us the importance of a very well planned field work and a very well recorded observations in the field, because in many situations we will see different generations of quartz veins occupying in different sets of fractures or any kind of structural weak planes, or different generations of mineralization or mineralizing veins, and then those kind of field work have to be really done in a systematic way, keeping in mind that we will be studying fluid inclusions in them. So, this is a good idea to begin with when we our study of fluid inclusion petrography. So, it is much like petrography done in a rock. When we do a petrography, why I say that much like a petrography done in a rock, because in a rock, if we make a thin section, our first objective is to identify all the minerals. So, whenever we do a normal petrography of a rock, the first thing that we do is that we identify all the minerals that is present in a rock, and then the next job at hand is to understand the time relationship between the different minerals, and this exercise at hand is exactly that we must be in a position to identify the inclusions in the minerals. When a beginner starts to study fluid inclusions, it sometimes becomes difficult for him or her to even distinguish a fluid inclusion from a mineral inclusion, and this is the very basic part of it, that a fluid inclusion and a mineral inclusion must be distinguished. So, a mineral inclusion in any case, when we go to look at it at a higher magnification, see the interference color, see the anisotropism, and it generally will be more distinct in that stage, whereas a fluid inclusion, as we discussed, it will be distinctly different, or it will be optically very distinct within the host mineral, and also it is typical whenever they present in the typical biphase like a liquid plus vapor. A mineral will never occur in that kind of a form, and or a 2 liquid plus vapor. So, only the scenario in which a mineral inclusion and a fluid inclusion could possibly be confused only in the case of the monophase inclusion, which is a little bit of a if not rare, but infrequent. So, the inclusions have to be identified. So, the inclusions, some of the inclusions which we have, by this time we have seen photographs of so many inclusions, we see that they can be very well identified. A liquid vapor biphase inclusion could be very well identified, or if there is a solid crystal lying in the inclusion cavity can be identified, and even though it is not likely to display exactly the optical characteristics by in a crossed nickel because of the very small quantity that is there or the transparency in the inclusion host, but still sometimes it is possible. Then so, when we are studying a fluid inclusion section, by the time we finish studying the fluid inclusion section, it is expected that we should have identified all the types of inclusions that is occurring in that particular sample, particular wafer. And then the mineral wise occurrence of fluid inclusions means, if we are not studying a material which is monomineralic like a quartz vein, sometimes we study fluid inclusions in metamorphic rock consisting of many of the metamorphic minerals like garnet, clinopyroxene, or sometimes even cordierite or other scapolite or some other mineral in which we can see fluid inclusions. Then it is very essential that we make a one-to-one correspondence between the inclusions and their host. If it is a polymineralic aggregate, then the paragenetic sequence of the minerals have to be well documented. Whether it is suppose for example, we are studying an ore specimen in which there is quartz, there is calcite, there is fluorite, all these three minerals are hosts for fluid inclusions, then their paragenetic sequence should be very well established, so that the fluid inclusion characteristic can be correlated and can be compared to see what exactly was the path of evolution of the fluid. So, the classification into different types based on observable phases at room temperature, and the broad classification to primary and secondary. Now, here the situation which needs to be closely looked into is the classification into different types. Generally, what happens that there is a practice that it's inevitable, it's invariably true that if we look at the host minerals from wide diversity of geological situations, it would be hardly or rare to see only one type. That means, for example, only a liquid plus vapor biphase inclusion or only a pure carbonic inclusion. It will always the rather rule other than exception that a host mineral will have a varied types of inclusions, and it is essential to before we conclude the petrography, fluid inclusion petrography, that we classify them into different types like type 1, type 2, type 3 and type 4 based on what their phase room temperature, phase assemblage and composition is. In this context, it should be important. So, for example, we are seeing aqueous biphase inclusions. So, for example, we are seeing aqueous biphase inclusions. I'll suppose this is one inclusion, and here there is another inclusion where now these two inclusions have visibly different proportion of liquid and vapor. Previously, many of the workers even prefer to measure, because we know that there is a big uncertainty there, we do not see the third dimension. So, that is the reason why we cannot immediately jump into a conclusion as to what could be the. So, and these inclusions generally this situation is described with a parameter which is called the degree of fill, which is essentially the volume of the vapor divided by the total volume of the inclusion, or I would say the volume of vapor plus volume of liquid. Since we have already seen inclusions are of the very wide diversity in their shapes and sizes, in at least the shape, and what would we visibly be seeing as variable this degree of fill or the vapor by vapor plus liquid ratio. It is not wise to classify these. Suppose these are the inclusions which are occurring, and suppose we follow a hierarchy. It is always a good practice, because in any particular host that we are studying the fluid inclusion, when we see say n number of types of inclusions, 4 types, 5 types of 6 types, all of them could, it is not possible that all will be occurring in equal population. There will be definitely difference, and some particular type would be more dominant or occurring in greater population than others. So, it would be easier to name them the first type, which is the most dominant type, could always go as the type 1. Let us say, for example, we see that in a host mineral there are aqueous biphase inclusions in this L plus V. We can identify them, they are aqueous biphase inclusions. So, you could put, and they are possibly the dominant type. So, we say that okay, they are the type 1. Either we could put as Roman 1 or numerical 1 like the type 1 or type 1. Sometimes they are putting a type 1, 2, 3, 4, or you can even say type 1, 2, 3, 4. Many times it is observed that this is more used by fluid inclusion workers. So, suppose that this becomes this is our type 1 inclusion, which is a liquid plus vapor biphase inclusion. It would not be good practice to further classify them into type 1A or 1B by saying that we are visibly seeing one vapor to be smaller and the other vapor to be larger, because as we will see later, this particular ratio, which is your vapor by vapor plus liquid ratio, is very well calculatable once we do the microthermometric experiments. And another important point also to remember is that by making a lot of further subclasses, classification only complicates the picture, and at the end of it we are going to represent the fluid inclusion data with respect to their different inclusion types and their microthermometric behavior. Having said that, there are situations in which some very exotic type or some very special type of inclusions may be occurring. They may possibly be documented and can be assigned a type. So, the classification into different types based on their observable phases at room temperature is a practice which is followed. And so now the major or the most important aspect of fluid inclusion study, which generally is fraught with a lot of uncertainties or lots of question marks, sometimes is put that the broad classification into primary and secondary. And we know that primary inclusions are the ones which are supposed to be the ones which are entrapped during the primary growth of the host mineral, and the secondary inclusions are the ones which were trapped anytime afterwards in response to fluid activity in weak planes, in fracture planes, which generally result in the sealing of the crack, and then they are present as trail bound inclusions. And one thing also to be kept in mind, that these processes also also sometimes happen at very greater pressure temperature conditions, and we can see that they are a phenomena which is not just very superficial. And so this broad classification to primary and secondary is the one of the challenging jobs in fluid inclusion petrography. Now, what boils down to the fact that when we see them, then we can only possibly, so the time relations amongst the primary and secondary, even it might so happen that we may see primary inclusions, but they may be of different generations. In the same quartz, there may be the quartz could have grown in different stages, and there are primary inclusions. If we are defining the primary inclusions to be the ones which occur in a random 3-dimensional network without being aligned on any trail or any heel crack, and then what actually sometimes becomes the practical thing when somebody is doing a fluid inclusion petrography, then to look for or to describe the inclusions, whether they are trail bound or non-trail bound, and if they are trail bound, whether they are present in transgranular heel cracks or intragranular heel cracks. As we know that the ones which are present in something like, if this happens to be the grain of quartz, and there are inclusions which are just trapped in this kind of a trail, and this trail is not transgressing into this adjacent grain, is terminating within the grain itself, and we have labeled them or designated them with a term called pseudo secondary. So essentially pseudo secondary means primary, means they look like secondary inclusions, but they are not secondary inclusions. So the fact remains that during the petrography we can only describe them, and when whether they are trail bound or non-trail bound. If they are trail bound, then if the trails are transgressing through many grains in the host mineral, means almost the entire section, entire FIS that we study, we could still trace the heel crack. So it is always so these are the way that we can go on describing, but it is a fact that so fluid inclusion petrography is the backbone of the fluid inclusion study. Before we go for fluid inclusion microthermometry, it is expected that the fluid inclusion petrography should have been done very meticulously, but the fact remains that many a times even some of the inclusions which could have been wrongly identified, which happens in mostly the cases of aqueous carbonic inclusion, where an aqueous carbonic inclusion by virtue of its irregular geometry may be wrongly classified as an aqueous biphase, but only when we take them to the heating freezing stage and lower the temperature, then sometimes we find that, well, what was essentially, so those kind of corrections of course has to be made, and they do not hamper the work or they do not affect the work in any serious way, because finally when the data are being presented, they are being presented as belonging to that particular class. So we will see what exactly a fluid inclusion section is, but the fact remains that all our description will be based on these kind of parameters. So as far as the fluid inclusion petrography is concerned, there has been many ideas that have been proposed by many different workers. The experts are who are the proponents or pioneer workers in the field. There was a concept which was given by Jacques Touré, as a group of synchronous inclusions. Means as if we are, as we all know that inclusions which we are seeing in a 300 micron thick fluid inclusion section, and we will be getting focused at different depths in terms of tens of microns when we lower or raise the microscope stage. So, different planes get focused containing the fluid inclusions, and there was a possibility which is raised that okay, any of these group of inclusions which are actually being observed as on occurring on the same plane and not following any of the trails could possibly be trapped at the same time and are synchronous to each other, and it could be possibly be mapped on a, if we think that we are taking this kind of a section, fluid inclusion section, and we can always put the positions of such kind of individual inclusions and label them as per their microthermometric response. Now, but we know that experience has told that it is not always possible, even if there are two inclusions which are occurring in the same grain of a host mineral not being trail bound, they may not also be trapped at the same time. So, that is why we will go into the details of discussion when we pick up the respective individual case studies. Rather, the concept of fluid inclusion assemblage is a little bit more practicable and is a more realistic way of doing a fluid inclusion petrography and describing the inclusions. Means in the same field of view, when I am not seeing the inclusions all of the same type. For example, I have seen inclusions in my samples where there are aqueous biphase inclusions, where there are aqueous polyphase inclusions, not considering the very special type of polyphase inclusions which are where the daughter crystal is a accidentally trapped daughter crystal rather than actually precipitating from the fluid. This also we will elaborate it later. For the time being, let us think that in a particular field of view or in a particular host mineral, when we are changing the field of view, we see many different types of inclusions and they may be occurring on the same plane. So, it is always better to describe them in terms of fluid inclusion assemblage, that what are the fluid inclusion types that I am seeing in my sample. Hierarchy that I am talking about, the following in the classification of fluid inclusions is in terms of actually the population. The most populous type should be given the first type. In my section, if it happens to be the aqueous carbonic type to be the most dominant type, so it will be, I will put them as a type 1 as aqueous carbonic, and the aqueous biphase may be occurring in less number and so on. And also one of the another point during the fluid inclusion petrography which should also be remembered, say aqueous biphase inclusions, they are occurring both as primary, that means occurring as part of the random 3-dimensional network, and also occurring as trail bound. It may not be a very good practice to say that well type 1 is primary and type 2 is secondary. It should be avoided, because type 1 inclusions which are, if when depending on the nature of the problem, suppose I am only interested in sampling the primary fluid and I am using the primary fluid inclusion aqueous biphase inclusions, but there are secondary heel cracks in which the similar aqueous biphase inclusions are there. It is possibly good to describe that these inclusions occur as both primary and secondary, and then depending on my plan of my fluid inclusion microthermometry, I can do thermometry on both these primary and the secondary type and can present them in different ways just to distinguish them whether the fluid that I am sampling is same or different. Well, so these are some of the very general preliminary ideas of such a very vast and pretty complicated topic which is fluid inclusion petrography. Sometimes it was suggested that to document the fluid inclusion petrography in well done hand sketches, written sketch of the fluid inclusion the way they are occurring, but to my belief at the present time with very good quality high resolution camera and the image compilation and stitching kind of software that we have, it is absolutely easy to even represent a whole thin fluid inclusion section in terms of the occurrence of the different inclusions in different parts of it, and can have a full idea, because it actually will be more it will be reliable, it will be anyone can see it and believe it, rather than actually going on doing it under hand sketch. Hand sketch is possible, it is not that it is to be discouraged, but a more practical way of doing it is capture the images, high resolution images, where the inclusions are identifiable and can be, each of the frames could be joined into a mosaics or could be stitched them, and can give us a very good idea about the occurrence of the fluid inclusions in the sample, the fluid inclusion section. Okay, so I will just very quickly browse through what I have said. So here we could see that what we understand by fluid inclusion assemblies. A typical example of fluid inclusion assemblies, which is which I have taken from the work that was done in our lab. So for example, in this situation in A, I am seeing only the aqueous biphase inclusion, only the type 1, whereas in the just figure which is beside that, the type 2 and type 3 inclusions are all occurring side by side together. And even in case of the photograph over here, type 3, type 4 and type 2 are all together here. And this image that I am showing here, it also gives us a good idea. Say for example, if you look at this C, and there are two places where the part have been blown up and the inclusion occurrences have been shown. So what is actually and that is the same case where you could see the inclusion F, where, so it is always a good practice to start looking at the fluid inclusion section at first at a lower magnification, to look at the where the grains are, so whether it is a recrystallized aggregate, whether it is a grain with pretty much interlocked and anhedral kind of grains interlocking, and the distribution of inclusions in the grains, whether the inclusion population is more in the core or in the rim, and even some of the cases even the zones are also there, sometimes also the zonal arrangement of the fluid inclusions also come out pretty clear, as the picture that I showed in the very first introductory part of this lecture series. So it is always good practice to start with low magnification, do a good prepare a good map of the section, and then describe the inclusions. And it is also easy to see the transgranular cracks, heel cracks that transgressing through the adjacent grains, and not only just one, even all the sets of such inclusions. So in this context, I have intentionally not mentioned about another way of describing these inclusions, which is essentially the concept of a fluid inclusion plane, which we will discuss when we discuss the application of fluid inclusion to deformation. So the fluid inclusion with the samples, when they are collected with the oriented section from the field, it is also possible to classify the inclusions into occurring in different planes, and the concept of fluid inclusion plane has also become quite popular. So the classification is accordingly done, and say for example, I have only given the case of some of the very regular type inclusions, like a type 1 could be aqueous biphase, as I told that the hierarchy could be different depending on the inclusion population. Type 1 is aqueous biphase, or type 2 is aqueous, like the one which has been shown here. Type 2 is aqueous polyphase, or type 3 is pure carbonic, type 4 is aqueous carbonic. But it may so happen that sometimes you may get a very special type of fluid inclusions, which the photographs I will show, and they need to be categorized irrespective of the fact whether their microthermometric data is being used or not, but they do represent some special circumstances. Say for example, inclusions containing graphite, which I will be showing later. So the good practice for the classification is that it should be simple, because it is to be correlated with the microthermometric data. At the same time, the information should be very properly represented. The fluid inclusion sections just as an example. This is taken from and just to show that how the fluid inclusion work actually begins from the field. So, this has been taken from the Eastern Ghats mobile belt, the granulate Eastern Ghats mobile belt, the gneissic basement, and there are different generations of melts that are generated and present is on form of leucosomes. So, a proper field study will definitely be able to delineate. For example, here the gneisses have their the leucocritic bands, and the later on they have been offset by the shear. So, these kind of field features are to be, if we are addressing a problem of evolution of the mobile belt in terms of the basement and the later phases of deformation and the generation of the different types of migmatites, then it is very essential that we make a very good observation in the field, correlate them with the observable structural episode. For example, this particular gneissic layering has been offset by a later shearing, and that temporal spectrum has to be identified. And suppose these are the first generation of the melts, they are the second generation of melt which can be identified from petrography, of course, and there are, suppose there are 3 different generations of melt, and we see them as leucosomes, sometimes conforming to the gneissic layering, sometimes to the shear planes, or sometimes getting into the boudinaged necks of the existing rocks. So, each has to be properly sampled, and then I will just give you an example what I understand by a fluid inclusion section. So, as you see here, as I discussed before, that we generally make a fluid inclusion section which will be at least about 3 centimeter to 2.5 centimeter square section, but the fluid inclusion stage, the photograph which I showed, will not be able to accommodate the entire section. It is also not advisable to put the entire section into it, because it will be difficult to do that. So, now this particular fluid inclusion section has been divided into different fragments for the ease of. So, not only just for ease of doing the microthermometric analysis, but also in terms of occurrence of fluid inclusions in different parts, which could very well be labeled. Okay, this part has this type of, for example, the arrow shows here, they show the occurrence of the pure carbonic inclusions in forms of cluster as well as 12 bound, and some other part there are pure carbonic inclusions occurring as part of the 3-dimensional network, there are vapor carbonic inclusions, and so this entire fluid inclusion section, once it is fragmented, can also be reassembled and labeled as part 1, 2, 3 for whatever is convenient, and then the fluid inclusion occurrences could also be indicated as to which. So, these are the chips that we break out of the fluid inclusion section, and for that they could be accommodated in the stage. It is not only that, one of the very practical aspect of fluid inclusion study which I will be just discussing. So, this is one example of fluid inclusion section and the way that fluid inclusion petrography has to be conducted, has to be carried out. This is also another one. Suppose we see the different types of, as we discussed, that there are 3 generations of melts. So, if we say that, well, the latest generation of melt is characterized by some type of very specific type of fluid inclusions, then it is quite obvious to expect that this particular type to be occurring as trail bound or secondary inclusions in the immediate earlier phase of the leucosomes that we are seeing. And as I was discussing, there are situations in which we could be seeing some very special type of occurrence of fluid inclusions, like here we could see that this particular inclusion contains graphite, which is confirmed from a later type of study. So, this contains graphite. So, this definitely has to be documented, that they may not be a lot more or occurring in very high population, like the one which is here is a. So, this occurs in the latest phase of the leucosomes that in the Eastern Ghats mobile belt migmatites, and they contain, and this particular latest stage of fluid is very much characterized by this. So, we will again come back to this case study when we discuss applications of fluid inclusion results to study metamorphism and such kind of complex complexly deformed and metamorphosed terrain. So, these for the brevity of time I am just skipping this now for the time being. And the last so now this fluid inclusion petrography in many of the places now wherever the facilities are available is being correlated with the cathodoluminescence study of the sample, and this cathodoluminescence study is only being done on quartz, and the quartz shows variable luminescence based on the trace element contents like aluminum and titanium, and it can be but since there is essentially is a surface feature and they dependent on the aluminum and titanium content, and quartz is an inherently weakly luminescent mineral compared to the carbonate and other minerals like zircon. Very such kind of studies are not that very widely successful, because it also depends on a very optimal combination of the experimental parameters to get good cathodoluminescent images. So, they are supposed to reveal the different growth zones in a quartz grain or different domains. I will just finish this discussion with a very specific case. Say for example, this inclusion is an is a vapor carbonic inclusion which homogenizes into vapor. This inclusion is an is a carbonic liquid inclusion. If we look at the phase diagram of carbon dioxide, coexistence of liquid carbon dioxide and vapor carbon dioxide corresponds to very low temperature situation in which neither any primary growth nor any recrystallization is expected. So, one would suspect that possibly these liquid carbonic inclusions were trapped early, and later on these vapor carbonic inclusions were trapped because of some recrystallization of the host mineral. And this diagram, which has been taken from the from literature from Kerckhoff, Vanden, Kerckhoff and Hein, it very clearly shows that this is a host mineral of quartz, and there is an inclusion over here, and this is a recrystallized domain of the inclusion which is present. So, this kind of situation is very possible. So, cathodoluminescence does not always result in very practically useful result, but sometimes they can also indicate very useful situation like this, where we can say that cathodoluminescence can come to a big way. It can help establishing the time relationship between fluid inclusions, which is a part of the fluid inclusion petrography. Here these pictures are also taken from Vanden, Kerckhoff and Hein, and you see this is a normal optical image where of the host quartz, where inclusions are occurring in such kind of a trail, and a cathodoluminescence is very nicely revealing the recrystallized the part of the quartz which has a different luminescence than the surrounding, which clearly indicates that they are different generations. But then the question is that when we take it to a microscope stage or a microthermometric stage, where we see them only in a higher magnification, where such kind of cathodoluminescence or such kind of zones, the spatial or the dimension sometimes should be much different, and the actual thing can be lost, that exactly which inclusions were corresponding to which zone. In summary, the cathodoluminescence is definitely can be taken help of wherever the facility is available, but a fluid inclusion petrography, if very meticulously done and also microthermometry to be followed, it can always compensate for the deficiency because of non availability of cathodoluminescence study. So, coming to the concluding part of it, that the fluid inclusion microthermometry has to be well planned. So, that means the questions that are generally coming to a beginner's mind is how many samples to study, how many inclusions to study, and which inclusions to study, primary or only both primary and secondary, or what to do first, freezing or heating. We will definitely be using this. So, there is no straight cut answers for that. It may sometimes be that if there is a good fluid inclusion section, at least 30-40 inclusions per fluid inclusion section should be sufficient. It must represent all the types that have been observed in that particular FIS, and then when such kind of samples are taken in good number from an exposure depending on the nature of the problem, because if I have, suppose for example, an ore deposit, an ore body which is measuring in terms of hundreds of meters or at least a kilometer. So, I would expect that at least some 30-40 samples and which is being studied, and at least some 30-40 inclusions per sample, so which will make a number to take care of the statistics. Sometimes to talk about the, as we will be seeing them in later classes, the fluid inclusion data interpretation is also very much dependent on the number of inclusions studied, and this is one methodology where the actual quantity of data is also very important. And the coming to the answer to the last question, so which inclusions, so primary only or both primary and secondary, is absolutely dependent on the problem being addressed, what exactly is the objective that is defined, whether to trace out the fluid activity in all the different stages of the in the particular geological environment, or sometimes if the work is the objective is towards understanding the different stages of deformation, then it is certainly the different fluid inclusion planes containing different types of inclusions have to be studied. So, in that case there could be secondary inclusions. So, now the answering to the question as to what to do first, it is always the advisable to go for freezing of the inclusion first, because of the fact that sometimes because of heating or overheating the inclusions characteristics are changed or inclusions are destroyed. This point will also be elaborately discussed in later classes when we will be taking up the case studies. So, with this kind of background information on the fluid inclusion characteristics, the principles of microthermometry, and a little bit of fluid inclusion petrography, we would move over to the subsequent lectures in this series, which will be talking about the heating freezing behavior of different types of inclusions and what kind of information can be retrieved from them, and what kind of conclusions could be arrived as far as addressing the broader geological problem. So, thank you very much. We will continue in the next week. Thank you.